Welcome to the ultimate guide for mastering your next AI operations interview. Are you getting ready for a cutting-edge role in artificial intelligence, machine learning operations, or large language model deployment? In this video, we're bringing you 200 expert-level, enterprise-grade interview questions and answers, covering everything from ML Ops basics to advanced LLMOps incident management, compliance, scaling, reliability, and real-world production challenges. Whether you're an engineer, a data scientist, or a tech leader looking to sharpen your skills and stay ahead in the rapidly evolving world of AI, these questions will empower you to tackle any technical interview with confidence. If you're serious about landing top AI roles or leading teams in the age of generative models and advanced automation, make sure to watch through, add your insights in the comments, and subscribe for even more industry-leading content. Now let's jump into the essential questions and answers every modern AI professional needs to know. What is ML Ops? ML Ops, the machine learning operations, is the discipline focused on productionizing machine learning workflows. It unifies the practices of machine learning systems development with operational processes such as CI and CD, monitoring, and model management. ML Ops ensures reproducibility, scalability, and governance by using tools and frameworks that automate the model lifecycle, from data acquisition and training to deployment, retraining, and monitoring. The focus is to bridge the gap between data science and IT operations, supporting reliable, secure, and compliant deployment of ML solutions in real-world scenarios. How does ML Ops differ from traditional DevOps? DevOps emphasizes streamlining software development and operations for rapid, continuous, and reliable delivery of applications. ML Ops, while inheriting DevOps automation principles, addresses the unique challenges in ML, such as data and version drift, experiment tracking, data pipelines, and reproducibility of code data model triplets. In ML Ops, the lifecycle adds complexities such as data versioning, feedback loops, hyperparameter tracking, model monitoring, and automated retraining, making it crucial for dynamic, data-driven products. What are the key stages of the ML Ops lifecycle? The ML Ops lifecycle includes data acquisition, pre-processing, feature engineering, model training, validation, deployment, monitoring, and retraining. Each stage emphasizes automation, ranging from continuous data validation to rolling out model updates triggered by performance drops. Feedback loops close the cycle, integrating user and system feedback for retraining. Version control is present throughout, vital for transparency, reproducibility, and auditability. What is model drift and how do you handle it in production? Model drift is the phenomenon where a model's predictive performance declines due to shifts in real-world data distributions, like data drift, or changes in the target relationship, like concept drift. Handling drift involves continuous monitoring of model metrics, triggering alerts when thresholds are crossed, and automating retraining with fresher data. Techniques include statistical tests for input feature drift and business KPI monitoring for output drift. Tools such as Prometheus, Grafana, or custom dashboards support real-time alerts. Canary deployment and A/B testing minimize risk with new versions. How do you ensure reproducibility in machine learning experiments within an organization? Reproducibility is enforced by strict version control of code, data, and feature engineering steps, typically using tools like Git, DVC, and MLflow. Every experiment run, with its code, versions, data sources, random seeds, and hyperparameters, is logged and tracked. Environments are isolated and containerized. Examples are Docker, Kubernetes, ensuring portability and consistent results. Documentation, notebooks, and experiment tracking platforms support audit trails and collaboration. Explain the role of MLflow, Kubeflow, or DVC in ML Ops. MLflow manages the end-to-end ML lifecycle experiment tracking, model packaging, deployment, and registry management. Kubeflow orchestrates scalable ML workflows on Kubernetes. It supports distributed training and pipeline automation. DVC, data version control, enables dataset and model versioning, ensuring reproducibility and scalable collaboration for large data artifacts. These tools automate experimentation, promote best practices, and lower operational risk. How do you design and implement a CI and CD pipeline for ML? A CI and CD pipeline for ML integrates continuous code and data validation, automated builds, training, testing, packaging, and deployment. It runs unit tests for code and data, triggers training on successful merges, validates new models against acceptance metrics, and automates containerization for deployment. Model testing and staging/production is followed by approval gates. Monitoring and automated rollback mechanisms are included for resilience and safety. Compare online and batch model serving in production. Online serving responds to real-time requests, example is fraud detection, and emphasizes low latency, high availability endpoints. Batch serving processes large data sets on schedules, example is nightly recommendations. Online inference needs robust API management tools and monitoring for traffic spikes, whereas batch inference relies on scheduled jobs, distributed processing, and cost optimization. Real-time use cases require strict monitoring and autoscaling for quality of service. What is blue-green or canary deployment in ML Ops? Blue-green deployment maintains two identical environments, one live and one idle, blue and green. A new model version is deployed to green, tested with live traffic, and traffic is switched if stable. Canary deployment routes a small subset of users to a new version, monitoring real-world impact before full rollout. Both methods limit risk when shipping new models and simplify rollback if issues arise. Describe multi-cloud or hybrid ML Ops deployments with relevant challenges and solutions. Multi-cloud/hybrid ML Ops spans multiple cloud providers or combines on-prem and cloud resources for resilience, flexibility, and avoiding vendor lock-in. Challenges include data transfer/latency, consistency in pipelines/model registry, managing dependencies across clouds, and cost optimization. Solutions involve containerization, Docker, Kubernetes, cloud-agnostic tools, Terraform, unified monitoring/logging, and automated compliance measures. Designing loosely coupled portable workloads helps streamline these setups. What are the main challenges ML Ops addresses compared to ad hoc ML development? ML Ops tackles multiple challenges inherent to traditional ad hoc ML workflows. Without ML Ops, teams often struggle with tracking data and model versions, lack automated deployment, and find it hard to reproduce experiments. ML Ops frameworks introduce robust experiment tracking, reproducible workflows, data and model versioning, automated CI and CD pipelines, scalable deployment, and continuous monitoring. This structured approach reduces manual errors, improves collaboration across teams, and ensures models are reliable, compliant, and production-ready, even as requirements or incoming data evolve. What is data drift, and why is it important to monitor it in an ML Ops setup? Data drift occurs when the distribution of input data changes over time, potentially causing predictive models to become less accurate because their training data no longer reflects the current environment. Monitoring for data drift is vital because even if a model was effective at launch, business or environmental changes may make it obsolete. Automated drift detection and responsive retraining pipelines ensure model performance is maintained, while alerting teams when intervention or analysis may be needed before the business impact is significant. How does DVC enable better collaboration and reproducibility in ML teams? DVC enables ML practitioners to version large datasets and model artifacts alongside code, much like Git, but for data. This means every data transformation, feature set, and model file generated can be tracked, shared, and traced back to its origin. Teams working together can always access the same data and model versions, instantly reverting to previous states when required. DVC pipelines also document every step of the workflow, further aiding reproducibility and transparency, essential for auditability and regulatory requirements. What is a model registry, and what is its significance in ML Ops? A model registry is a centralized, structured repository where all trained models and their metadata, such as version, parameters, metrics, and stage, examples are DOT, staging or production, are stored. It's significant because it supports lifecycle management, facilitates comparison, enables rollback to previous versions, and coordinates deployment flow. Registries are critical for organizations scaling ML operations as they support traceable, auditable deployment history, enforce access controls, and align with CI and CD systems to automate transitions between development and production. Contrast the practice of A/B testing and canary releases for new ML model versions. A/B testing deploys two or more models simultaneously to different user segments, collecting feedback and performance data to compare model behavior in parallel. This helps teams measure how a new model impacts user experience or business goals versus the old one. Canary releases, meanwhile, direct only a fraction of production traffic to the new model, gradually increasing exposure if performance is stable. Both aim to minimize risk and enable data-driven decisions, but A/B testing is more focused on side-by-side model comparison, while Canary is about cautious, incremental replacement with automated rollback if issues are detected. What are some best practices for setting up monitoring and alerting on ML models in production? Best practices include monitoring both technical and business metrics, such as latency, throughput, accuracy, precision/recall, drift scores, and user KPIs. Set automated thresholds and alerts for anomalies. Deploy observability tools like Prometheus or Grafana for dashboards. And log not only predictions but also input features to diagnose causes of drift or failures. Integrate feedback loops so that alerts trigger investigation, retraining, or automated rollback, ensuring minimal business disruption and continuous performance optimization. How do feature stores contribute to MLOps workflows? Feature stores serve as a centralized repository for curated, reusable features that power machine learning models across an organization. By registering features once and making them universally accessible, teams avoid duplicated engineering work, reduce data leakage risk, and promote feature consistency between training and serving. Feature stores also version features and document their lineage, so updates and corrections are tracked for compliance and reproducibility, benefiting regulatory audits and model governance. Explain the importance and techniques of data validation in automated ML workflows. Data validation ensures that incoming data entries match expected formats, ranges, and schemas before being used for model training or inference. Automated pipelines employ tools like TensorFlow data validation or Great Expectations to validate data continuously, flag anomalies, or trigger rollbacks when data quality issues arise. Robust validation reduces risk of production errors, enforces business rules, and provides early warnings of data pipeline issues, maintaining trust in deployed ML systems. How do you ensure security and compliance during the ML model lifecycle? Security is ensured by controlling access to data, models, and pipelines, using identity management, robust role-based access policies, and network segmentation. Compliance involves data anonymization, logging all access and inferences, and implementing audit trails for each stage of the pipeline. Automated tools can help detect unauthorized changes, while governance platforms ensure models adhere to regulatory, fairness, and explainability standards, crucial for sectors like finance or healthcare. What strategies can be used to ensure explainability in deployed ML models? Explainability techniques include using interpretable models, like linear or tree-based models, applying tools such as LIME or SHAP for post-hoc explanations, and visualizing feature importance. Documentation and user-facing dashboards help communicate decisions to non-technical stakeholders. For regulated industries, model explainability artifacts are stored alongside models for audit readiness. The approach balances transparency, regulatory requirements, and the technical complexity of modern ML models. How do microservices architecture benefit ML ops deployments? Microservices architectures break down ML workloads into loosely coupled, independently scalable services. Data ingestion, pre-processing, model serving, and monitoring can all run as individual services. This increases maintainability, allows independent updates, and makes it easier to introduce new models or change components with minimal risk. Using container orchestration platforms like Kubernetes ensures high availability, resource efficiency, and isolation between services, critical for enterprise ML ops scalability. Discuss the role of orchestration tools like Airflow or Kubeflow in production pipelines. Orchestration tools allow automated, robust management of workflow dependencies, scheduling, and execution for complex ML pipelines. Airflow makes it easy to define, schedule, and monitor multi-step ETL and model training jobs with error handling and logging. Kubeflow, integrated natively with cloud infrastructure, handles training, hyperparameter tuning, and deployment as scalable workloads. These tools ensure reliability and repeatability, reducing manual intervention, enabling versioned workflows, and supporting enterprise SLAS for ML services. Describe a robust approach for testing machine learning models before production deployment. Before deploying models, robust testing includes unit tests on feature engineering code, integration tests on the pipelines, and validation against a holdout dataset to check for overfitting. Simulation in a staging environment using production-like data is critical, as is stress testing for edge cases and performance bottlenecks. Shadow deployments, where the new model runs parallel to the live version but does not affect users, help identify hidden issues. Automated test suites and approval gates in CI and CD minimize the risk of promoting flawed models to production environments. How do you automate model rollback in the event of production failures? Automating model rollback is achieved through versioning model artifacts in a registry and integrating health checks or automated monitors into CI and CD. If a new model's performance drops or error rates spike, the system triggers a rollback, reverting to the last stable version with minimal downtime. Canary and blue-green deployments support this by allowing automated switchbacks without affecting most users. All rollbacks are fully logged and auditable for compliance and root cause analysis. What are the best practices for designing scalable machine learning data pipelines? Best practices include pipeline modularization, breaking workflows into small, composable tasks, containerization for portability, and distributing heavy workloads, like pre-processing or feature extraction, using Spark or Dask. Versioning every pipeline step enhances reproducibility and troubleshooting. Orchestration frameworks, Airflow, Kubeflow, are essential for managing complex job dependencies, and autoscaling based on data volume or resource utilization ensures efficiency and cost control as production demands grow. How do you manage and monitor pipeline failures in production? Pipeline monitoring is achieved with logging, real-time alerting, via Prometheus, Grafana, or cloud-native tools, and structured error handling at each pipeline stage. Pipelines are built with idempotent steps, retry on failure policies, and fallbacks for non-blocking tasks. Automated error notification, along with root cause and impact analysis, ensures rapid mitigation and continuous improvement, maintaining reliability in mission-critical ML services. How do you foster collaboration between data engineers, data scientists, and operations teams in ML Ops? Effective collaboration requires clearly defined roles and responsibilities, shared documentation, and communication frameworks. Using unified version control, standardized artifact registries, and experiment tracking, such as ML Flow or Neptune.ai, ensures transparency. Agile ceremonies, stand-ups, retrospectives, and feedback loops keep everyone aligned, while shared dashboards provide a single source of truth for model performance and pipeline health. Encouraging knowledge sharing and blameless post-mortems builds a culture of continuous improvement and trust. In your experience, what organizational challenges can impede successful ML Ops adoption? Challenges include siloed teams with conflicting priorities, lack of executive support for automation investments, and resistance to change from ad hoc workflows. Limited data governance, inadequate infrastructure, or unclear ownership of pipelines also delay adoption. Addressing these requires strong leadership, cross-functional buy-in, ongoing training, and quantifying the business value of ML Ops through clear KPIs and successful pilot projects. Institutionalizing best practices and celebrating early wins help embed ML Ops principles into organizational culture. How do you set up end-to-end model monitoring in production environments? End-to-end model monitoring includes tracking both system metrics, CPU, memory, request latency, and business metrics, accuracy, precision, recall, customer KPIs. Alerts are configured on key metrics that warn of degraded performance or outages. Collecting real-time data on model inputs and predictions enables drift detection while integrating dashboards. Examples are Grafana, Prometheus, or cloud-native tools, supports cross-team visibility. Pipelines trigger automated retraining or rollback if drift or anomalies are detected, and all incidents are logged for compliance and diagnosis. What approaches would you take to detect and handle concept drift in production models? Concept drift occurs when the statistical relationship between features and target variables changes, reducing model accuracy. Detection methods include tracking, declining prediction performance, using statistical tests like Kolmogorov-Smirnov on prediction distributions, and periodically collecting truth labels for retraining. When concept drift is detected, automated retraining pipelines kick in, often using recent data and validating new models against business acceptance criteria. It's essential to document all drift events and actions taken for regulatory and process improvement purposes. Describe the role of automation in achieving self-healing ML Ops pipelines. Automation allows pipelines to respond rapidly and autonomously to common failures, such as data quality drops, pipeline failures, or model underperformance. Automated error detection and self-healing mechanisms, like retrees, fallback models, switching to cached predictions, or rolling back versions, reduce downtime and human intervention. Defining clear thresholds for errors and integrating incident response workflows ensure business continuity, freeing engineers to focus on improving rather than maintaining existing systems. What are the main strategies for minimizing downtime during automated deployment and retraining? Combining blue-green or canary deployments limits rollout risk by exposing only subsets of traffic to new models at first. Decoupling training and inference infrastructure enables retraining with no impact on ongoing inference. Automated rollback and versioning ensure a quick switch if issues are encountered, while careful scheduling of deployments off-peak hours, shadow testing in parallel, helps further minimize user impact. Health checks, redundant infrastructure, and failover configurations are essential for maintaining service availability. Walk me through how you would diagnose a sudden drop in model accuracy post-deployment. Diagnosis begins with reviewing model monitoring dashboards for performance metrics and incoming data characteristics. Checks include, has the data schema or quality changed? Are there missing values or distribution shifts? Are upstream data sources healthy? Next, retrain or roll back the model as needed, and if neither resolves the issue, escalate to detailed root cause analysis, reviewing logs, pipeline runs, configuration changes, and recent code deployments. All findings and mitigations should be documented for future reference and improved automated defenses. Can you share an example of a pipeline failure you encountered and how you resolved it? A common example is an upstream data feed breaking, causing the pipeline's data validation step to fail and blocking model retraining. Resolution involved alerting, examining logs to confirm the data outage, applying a fallback, using the last known good data set, and restoring service. Post-mortem actions included working with data engineering to add redundancy to feeds, improving monitoring granularity, and building automated quality gates for early detection. What are the best practices for ensuring auditability of ML pipelines in regulated industries? Auditability requires complete, immutable logs of all pipeline activities, data ingestion, pre-processing, training, validation, deployment, and inference. Every step must be versioned and time-stamped, including code, data, model artifacts, and environment details. Implementing traceable experiment tracking, signed artifact storage, and detailed incident logging ensures that, in the event of an audit, any prediction or decision can be traced back to its origin, including exact model and data versions used. Integration with compliance tools and regular internal audits solidify regulatory readiness. How do organizations implement and maintain model governance frameworks? Model governance encompasses processes and tools that control model development, deployment, access, and lifecycle management. Organizations establish governance by enforcing change management protocols, pull request reviews, approvals, standardizing documentation practices, maintaining access controls on model registries, and aligning policies with regulatory requirements, such as GDPR, HIPAA, or SOX. Automated policy enforcement, example, restricting promotion to production without passing fairness or explainability tests, ensures organizational standards are continuously met. How do you balance cost optimization and performance in large-scale ML Ops deployments? Cost optimization starts with resource profiling, understanding when and where computation is needed. Example is spot instances for training, auto-scaling for inference APIs. Orchestrators like Kubernetes are configured with auto-scaling policies, and serverless frameworks are leveraged for event-driven tasks. Model compression and pruning can decrease inference costs. Continuous monitoring of cloud expenses, combined with architecture choices, batching jobs, offloading workloads to cloud when economical, helps ensure that scaling doesn't lead to runaway costs. What techniques have you used to orchestrate cross-region or multi-cloud ML workloads? Multi-cloud orchestration leverages containerized workflows with orchestration tools like Kubeflow, Apache Airflow, or managed cloud services. Data synchronization is handled through cloud-agnostic object storage with version control, and secure APIs maintain consistency. Latency is minimized by deploying inference endpoints close to users, while global load balancing and centralized monitoring ensure smooth cross-region operation. Hybrid deployment patterns like on-prem or cloud mix are increasingly common in regulated sectors, demanding careful attention to compliance and data locality laws. Describe how you would manage multiple versions of a model serving different business use cases simultaneously. This requires a robust model registry, tracking versions, signatures, and deployment metadata. Each model is registered with contextual tags indicating its use case, customer segment, or geographic region. Model routing logic within inference APIs directs requests to the appropriate model version based on headers or request parameters. Automated regression testing ensures that updates to one version don't impact others. Dashboard-driven monitoring tracks the health and business value of each deployed instance, supporting audits and continuous optimization. In an enterprise with strict regulatory controls, how would you integrate human-in-the-loop HITL review into your ML Ops workflows? HITL is incorporated by configuring automated pipelines to route predictions that don't meet predefined confidence thresholds or those involving sensitive data to designated reviewers. All manual review decisions and their rationales are logged and versioned for auditability. The ML Ops workflow supports feedback integration, so approved corrections are cycled back into retraining pipelines. This balances efficiency with regulatory and ethical requirements, ensuring humans remain accountable for critical or ambiguous decisions. What are the core security best practices for enterprise ML Ops environments? Core practices include encrypting sensitive data at rest and in transit, implementing strict access controls and role-based permissions, and maintaining audit logs for all model and data asset access. Regular vulnerability assessments, network segmentation, and using trusted execution environments for inference reduce attack surfaces. Model watermarking is increasingly adopted to protect intellectual property, and versioning of all code, models, and data ensures traceability in the event of a breach or unauthorized change. How do you protect ML models from adversarial attacks or model theft? Protection strategies involve controlling model access, private endpoints, secured APIs, encrypting and signing model artifacts, and using input validation to block adversarial requests. Model watermarking and obfuscation deter theft and replication. Routine monitoring for unexpected input or prediction patterns can help detect attempted evasion or poisoning attacks. For high-risk deployments, organizations may integrate differential privacy or federated learning to limit data exposure and strengthen defenses. What is a robust incident response plan for handling ML-specific security breaches? A robust plan starts with real-time threat monitoring, clear incident escalation protocols, and automated blocking of compromised endpoints or models. Forensics are performed to trace source, impact, and affected assets. Detailed post-mortem reviews update internal playbooks and automate new detectors for identified vulnerabilities. Restoration from a trusted backup or rollback point is combined with regulatory reporting, and all security events are logged for future audits. How do you ensure your ML workflows remain compliant with global data regulations? Compliance practices include anonymizing or masking personally identifiable information, limiting data retention based on local laws, and maintaining detailed data lineage and documentation of all processing activities. Aligning pipelines with standards such as GDPR, HIPAA, ISO 27001, or SOC2 is achieved via enforceable policies, audit trails, and collaborating early with legal risk and IT teams. Compliance is verified through periodic audits and regular training for all teams working with sensitive data. What role does continuous monitoring play in secure, trusted ML deployment? Continuous monitoring is essential for detecting threats, data drift, model performance anomalies, and unauthorized usage. Automated analytics flag suspicious activities or access attempts, triggering immediate incident workflows. Monitoring solutions also support business KPIs, providing evidence of security control effectiveness during regular compliance audits. This proactive approach ensures that systems remain resilient, trustworthy, and capable of adapting to evolving threats or requirements. Describe how role-based access control (RBAC) and audit logging are implemented for AI model governance. RBAC ensures that only authorized individuals can modify, deploy, or access models, datasets, and pipeline configurations by assigning granular roles to users and services. Audit logging records every access and change with metadata, user, time, asset, action, to create a comprehensive accountability trail. When combined, these enable fine-grained governance, rapid breach investigation, and evidence-based compliance for enterprises deploying AI at scale. What are the key principles for implementing trusted AI within ML Ops workflows? Trusted AI requires embedding transparency, fairness, security, and accountability throughout the ML lifecycle. Organizations must ensure model explainability using SHAP, LIME, or interpretable models, monitor for bias, and validate models for fairness before production. Documenting model assumptions, training data lineage, and limitations is crucial. Governance frameworks enforce regular reviews, change approval processes, and alignment with regulatory standards such as GDPR or ISO 27001, making trust measurable and auditable. How do automated CI and CD pipelines contribute to operationalizing responsible, trustworthy AI? Automated CI and CD pipelines enforce consistency across code, models, and data. Every build triggers standard validation, fairness/bias checks, and security scans. Pipelines include experiment tracking, model testing, and approval gates, reducing errors and ensuring models meet ethical and operational standards before live deployment. The automation of retraining and rollback procedures further reduces risk and accelerates trusted releases. Why is cross-functional collaboration critical to ML Ops success in the enterprise? Enterprise ML Ops spans data science, DevOps, security, compliance, and business units. Open communication and shared ownership ensure success. Integrated dashboards, shared model registries, and collaborative documentation streamline handoffs and feedback. When teams operate in silos, duplication, rework, and inconsistent models proliferate. High-maturity ML Ops organizations invest in collaborative process design, shared metrics, and regular cross-functional reviews to align machine learning outcomes with business value and compliance targets. What are the most important documentation and traceability practices to increase trust and auditability in ML Ops? Comprehensive documentation tracks every pipeline, model, and dataset version, including assumptions, feature definitions, and known limitations. Systems like ML Flow or custom model management platforms log every experiment, hyperparameter setting, and result. Audit logs record deployments, access, and changes. Automated lineage tracking enables auditors and teams to reproduce any result, explain any decision, and comply with evolving standards for transparency and accountability. How do you implement robust model governance in ML Ops pipelines? Model governance is multi-layered. It starts with versioning every model, dataset, and associated metadata, often inside a model registry. You must ensure that all model changes are auditable, with traceable logs showing who trained, approved, and deployed each artifact. Governance policies are enforced through automated pipelines that check for compliance with internal and external standards before promotion. Regular model audits, documentation, and monitoring for drift/fairness are built in. Collaboration between data science and IT is essential to manage roles, permissions, and access across tools like Kubeflow or MLflow, so issues are tracked and addressed promptly. Share a real-world scenario where you solved a complex ML ops problem. What were the challenges and solutions? In a recent enterprise project, the main challenge was integrating models trained on heterogeneous, region-specific data. Issues included inconsistent pre-processing, drift between training environments, and unreliable deployments. Solutions involve standardizing feature pipelines using workflow orchestration, implementing centralized monitoring dashboards, and running A/B tests regionally before full rollout. Cross-functional stand-ups improve communication, while iterative deployment, paired with continuous feedback and monitoring, ensured models stayed aligned with business and user needs. How do you integrate A/B testing and continuous experimentation into MLOps workflows? Start with precise experiment objectives and hypothesized outcomes, defining clear metrics for success. In production, deploy and route user traffic to multiple model candidates using controlled, phased rollouts. Example via TensorFlow, Extended, or TFX or Kubeflow. Experimental data is carefully isolated and logged, and automated analysis is done to determine significance and pick the optimal variant. All results are documented, and successful experiments trigger automated CI and CD deployment, reinforcing a culture of iterative, data-driven improvement and resilience against regressions. How do you ensure model explainability and address regulatory concerns for black box models? Techniques include selecting inherently interpretable models for high-stakes use cases, or applying post hoc methods, such as LIME or SHAP, for complex models. All explanations, assumptions, and feature importances are documented in living artifacts. Regular reviews with business stakeholders and legal teams make sure model decisions align with regulatory expectations for transparency and user rights. If a model isn't explainable enough to satisfy governance or compliance, alternatives or mitigations, like constrained models, are adopted. What's the biggest challenge in implementing ML ops at scale, and how do you address it? The largest challenge is cultural, aligning the priorities of IT, data science, and business. ML ops success depends on breaking down silos through shared tooling, clear ownership, and quantifiable business metrics. Regular cross-team communication, blameless retrospectives, and documenting both successes and failures establish trust. Technical solutions follow: unified pipelines, standardized registries, scalable architecture, and robust automation. But long-term sustainability requires buy-in at every organizational level. How do you ensure scalability and optimal performance of ML models in production environments? Scalability is achieved by dynamically allocating compute resources using container orchestration tools like Docker and Kubernetes for deployment and autoscaling. Load balancing distributes inference requests across replicas, and batching input data can improve throughput for high-volume cases. Leveraging cloud platforms ensures elastic scaling and cost optimization. Model-level optimizations, such as quantization, pruning, or converting models to lighter formats, ensure fast inference, especially for latency-sensitive applications. Continuous monitoring and regular load testing help maintain performance standards as usage grows. What metrics should be tracked to assess the performance of ML models and pipelines? Key metrics include traditional ML scores, accuracy, precision, recall, F1, ROC/AUC, along with latency, throughput, error rates, model drift, and resource utilization. Pipeline-specific metrics track data ingestion lag, pipeline step failure rates, retraining cycles, and deployment success rates. Business KPIs, derived from model predictions, should also be monitored to tie technical performance to organizational outcomes. Dashboards and automated alerts ensure that teams are notified immediately of anomalies or degradation. Describe how you would set up a robust monitoring system for a deployed machine learning model. A robust system uses tools like Prometheus and Grafana, or cloud-native equivalents, to instrument and visualize inferences, input distributions, latency, and model-specific metrics. Statistical tests detect data or concept drift, while business metrics are integrated for real-world validation. Alerting rules trigger when performance drops or drift thresholds are crossed. automatically launching retraining pipelines or rolling back models as needed. Logs are exported to a centralized, searchable location to support audits and postmortem reviews. What best practices can minimize downtime during model redeployment or drift-triggered retraining? Blue, green, or canary deployments allow new models to be tested safely with partial traffic before full rollout. Decoupling retraining infrastructure from serving endpoints ensures ongoing inference isn't disrupted by pipeline jobs. Automated health checks, versioned artifacts, and rapid rollback capabilities reduce the risk of failed deployments. Scheduling retraining during off-peak hours and maintaining redundant resources further ensure high availability. Comprehensive logs and incident playbooks streamline recovery in case of unexpected failures. How do you optimize pipeline performance and reliability for large-scale ML Ops workflows? Pipeline optimization starts with modular design, breaking up complex workflows into small, reusable components that can be independently tested, monitored, and scaled. Orchestration tools manage dependencies, retries, and error handling to ensure robustness. Caching intermediate results reduces redundant computation, while storing artifacts in fast, shared storage accelerates distributed processing. Parallelization through Spark, Dask, or cloud-native frameworks handles large volumes, and continuous integration and continuous deployment pipelines enforce validation and rollback standards automatically at every step. How do you detect bias in ML models deployed through ML Ops pipelines? Bias is detected using statistical tests and performance breakdowns across key demographic or categorical groups, such as gender, age, or geographic location. Automated tooling, examples are IBM's AI Fairness 360 or FairLearn, can calculate disparate impact, equal opportunity difference, and other bias metrics. Evaluation is integrated into pipeline validation, so every new model version includes fairness checks. If bias exceeds thresholds or changes over time, alerts are raised to trigger investigation or retraining with more balanced data. What practical steps do you take to mitigate model bias within an ML Ops workflow? Bias mitigation is addressed at multiple stages: pre-processing, resample or augment data to balance representation. In training, apply fairness constraints or regularization in the model objective. Post-processing, adjust predictions. Example are thresholding or reweighing outputs to equalize outcomes. ML Ops pipelines formalize these checks, automatic reporting, scheduled fairness audits, and documentation of mitigation steps. Regularly including domain experts in model reviews reduces blind spots and supports stronger real-world fairness. How do you audit and document decisions made by ML models in a production ML Ops setup? Comprehensive audits require logging all inputs, predictions, confidence scores, and, crucially, counterfactual explanations whenever a decision is made. Model and data versions, pipeline configurations, and feature lineage are tracked in registries and experiment tracking platforms. Automated reports summarize decision statistics per subgroup for transparency, while data and model access logs support after-the-fact investigations and regulatory requirements. How does continuous bias and fairness monitoring work in real-world ML Ops deployments? Pipelines regularly score and track fairness metrics on sliding windows of new production data. Alerts are triggered if significant performance or fairness gaps emerge over time. Retraining can be automated based on these alerts, but always requires governance review before deployment. The process ensures not just the initial fairness of models, but their ongoing equitable performance, enabling trust and compliance as environments change. Why is it important to consider ethics and stakeholder input in enterprise ML Ops, and how do you incorporate this? Ethical use of AI ensures not only regulatory compliance, but also upholds reputation and long-term value for organizations. Engaging with stakeholders like customers, legal, ethics boards, marginalized groups, during development and validation uncovers unintended harms or societal impacts. Workshops, reviews, and pilot programs inform requirements and establish boundaries. Transparent policies, clear documentation, and ongoing dialogue create a feedback loop to adapt ML Ops practices as both technology and context evolve. What is hyperparameter tuning, and why is it critical in ML Ops workflows? Hyperparameter tuning is the process of systematically searching for the optimal values of parameters that govern the learning process of a machine learning model, such as learning rate, batch size, or regularization strength. Effective tuning can dramatically impact a model's predictive power, stability, and generalizability. In ML Ops workflows, tuning is operationalized using automated tools or orchestrated experiments, ensuring every tuning run is tracked, reproducible, and easily compared. This systematic approach ensures efficient use of computational resources and supports model governance by auditing tuning decisions. What are common methods for hyperparameter optimization in large-scale ML pipelines? The most common methods are grid search, exhaustively evaluating every possible combination of predefined parameter values; random search, sampling random combinations across the hyperparameter space, often more efficient than grid search for large spaces; Bayesian optimization, using probabilistic models like Gaussian processes to predict promising regions of parameter space and balance exploration with exploitation; evolutionary algorithms, leveraging genetic programming to evolve hyperparameter sets across generations. Modern ML Ops platforms integrate these approaches to balance thoroughness and computational cost. How is automated hyperparameter tuning integrated into ML Ops pipelines for production? Automated tuning jobs are orchestrated as pipeline steps, powered by open-source tools. Examples are Optuna, HyperOpt, or managed services like AWS SageMaker Tuning, Azure AUTML. The pipeline manages configuration sweeps, tracks each run with experiment management tools such as MLflow or Kubeflow Catum, and persists the best performing model and its hyperparameters to the model registry. Tuning jobs are scheduled for new data or model changes and can trigger further steps, like deployment or shadow testing, when improvement is detected. Describe the strengths and weaknesses of grid search, random search, and Bayesian optimization for hyperparameter tuning. Grid search is exhaustive but can be computationally expensive and inefficient for large or continuous search spaces, as most combinations are rarely optimal. Random search is generally faster, more efficient for high-dimensional spaces, and avoids the curse of dimensionality suffered by grid search. Bayesian optimization is the most sample-efficient, learning from previous trials to predict where improvements will likely be found. However, it can become complex to configure and slower per iteration for very large categorical or mixed-type search spaces. How do you ensure reproducibility of hyperparameter tuning experiments within an enterprise ML Ops platform? Reproducibility is supported by tracking every experiment's configuration, random seed, input dataset, code version, and corresponding outputs with tools like MLflow or DVC. Checkpoints and artifact registries maintain all models, logs, and parameters, while containerization, Docker, and environment files record dependencies. Automated linking of runs, hyperparameters, and results ensures any experiment can be reconstructed or audited for validation, compliance, or further research. Describe a situation where ensemble methods would be particularly advantageous in an MLOps context. Ensemble methods such as bagging, random forests, boosting, XGBoost, or stacking prove especially useful when dealing with complex, heterogeneous data where individual models may have weaknesses. In a healthcare ML Ops setting, for example, combining models that specialize in lab data, imaging, and historical records helps produce more accurate and robust predictions than relying on a single model. In production, deploying an ensemble can mitigate risk by averaging out individual biases or errors, improving generalization and resilience against outliers or data noise. What are the main types of ensemble methods and how does each work? Bagging, bootstrap aggregating, trains multiple models on random subsets of the data and aggregates their outputs, reducing variance and overfitting. Random forest is a classic example. Boosting sequentially trains models, each focusing on correcting the errors of its predecessor, producing a strong learner from several weaker ones. Examples are AdaBoost, gradient boosting. Stacking combines predictions from diverse model types, base learners, using a meta model that learns how to best integrate them. Ensemble strategies are integrated into the ML Ops pipeline for improved stability, but they require careful orchestration for training, deployment, and monitoring multiple interconnected models. How do you monitor and update ensemble models in a production pipeline? Monitoring ensembles involves tracking overall performance as well as the individual components, alerting if a single submodel underperforms, which might signal data drift specific to a data segment. Retraining policies are automated for both the ensemble and its parts based on defined thresholds or drift detectors. Pipelines are set to log predictions, compare against ground truth, and trigger shadow tests or canary rollouts for updated ensemble versions, minimizing risk of regressions during online updates. How do you integrate a new advanced ensemble into an existing MLOps pipeline with minimal disruption? Start by reviewing the current architecture for compatibility and interfaces. Update data preprocessing and feature engineering steps if necessary. Test integration in a staging environment, running side-by-side shadow deployments to analyze impact without affecting live predictions. Update monitoring and logging tools to record ensemble behavior and set up alerting for new failure modes. Collaboration with both data science model logic and ops deployment. Monitoring teams ensures robust validation before switching traffic to the new ensemble in production. How do you foster collaboration between data scientists and engineers when deploying complex ensemble solutions in MLOps? Effective collaboration is built through clear, shared project goals and KPIs, regular cross-team meetings for status updates and troubleshooting, shared experiment tracking and model registry platforms like ML Flow or Neptune.ai, so every stakeholder sees the logic, data, and performance of ensemble components. Joint retrospectives after major deployments to improve communication and process. This coordinated approach reduces friction, helps align expectations, and leads to smoother, more scalable deployments. What are the primary strategies for retraining machine learning models in production systems? Retraining strategies include scheduled retraining at fixed intervals, example, weekly or monthly, event-driven retraining, triggered by drops in model performance or significant data drift, and on-demand retraining, like initiated by business changes or new data spikes. Some systems also use online, incremental learning for constant adaptation to data streams. Automated pipelines in MLOps coordinate these strategies, using performance metrics and drift detectors to trigger retraining and ensure models remain accurate and relevant. How do you automate model retraining in CI and CD for deployed ML models? Automation relies on robust CI and CD pipelines. They validate code and data, run automated tests, train models when updates occur, and deploy only if all validation checks pass. Retraining is linked to monitoring systems that watch for performance drops or data changes, triggering the pipeline without manual intervention. Pipelines use version control, rolling deployments, and thorough logging to ensure reliability and fast rollback if needed. Tools like Kubeflow, ML Flow, Jenkins, or cloud-native platforms orchestrate the full retraining lifecycle. What are best practices for validation and governance during automatic retraining? Governance demands pre-deployment validation. Each retrained model is tested in a staging environment against business and technical benchmarks. Snapshots of data and code are preserved for reproducibility. Approval workflows, manual or automated, ensure that only validated, unbiased, and compliant models go live. Governance also requires clear responsibilities, transparent reporting, and audit trails for all retraining events, so models are explainable and regulatory requirements are met. How do you manage risks associated with automated model retraining and deployment? Risks include silent model degradation, data pipeline failures, or biased retrained models. Mitigation is achieved through comprehensive monitoring, like model and data metrics, drift, errors, alerting for anomalies, and automated rollback mechanisms. Canary and blue-green deployments let you test retrained models with a subset of traffic before full rollout. Governance and human-in-the-loop checks act as final safeguards in critical workflows or highly regulated environments. How does online learning compare to batch offline retraining, and when would you use each? Online learning updates the model incrementally as new data arrives, offering rapid adaptation and low-latency use cases, but can risk propagating noise or concept drift without checkpoints. Batch retraining rebuilds models with larger, curated datasets, ensuring stability and thorough validation, but may lag behind real-world shifts. Online learning is preferred for scenarios with highly dynamic data. Example is fraud detection, while batch retraining is used for regulatory or mission-critical models that demand rigorous pre-deployment assessment. Describe a time when you had to troubleshoot a production issue with an ML model. A production issue surfaced when a deployed model's performance dropped abruptly. Troubleshooting began by examining logs and monitoring dashboards for anomalies, quickly revealing a change in input data distribution. Collaborating with the data engineering team, the data pipeline was found to be altered, affecting pre-processing. The solution involved updating the data preparation steps, retraining the model on the new data profile, and deploying with updated monitoring to promptly catch future distribution shifts. How would you approach integrating a new model into an existing MLOps pipeline? Integration begins with reviewing the current pipeline, ensuring all data pre-processing and feature engineering steps fit the new model. Rigorous testing is performed in a staging environment, validating both predictive performance and proper integration. Once verified, monitoring and alerting configurations are updated to include new features or behaviors of the model. Finally, thorough documentation and rollback plans are in place before full production launch to minimize disruption. If a model's performance degrades over time, what steps would you take? The first step involves analyzing model predictions and input data, checking for drift, changing patterns of user behavior, or errors in source data. Data and feature relevance are reviewed and tested. Retraining on recent data or refining the feature set may restore performance. Where practical, A/B testing can compare alternative approaches or retrain models before full deployment, ensuring that performance gains are real and not temporary anomalies. Describe a high-stakes incident where rapid root cause analysis was required for a failed batch inference job. In a mission-critical workflow, a batch inference job failed overnight, halting downstream reporting. The team rapidly inspected pipeline logs and cloud resource metrics, discovering a sudden spike in data volume that exceeded memory and processing limits. The pipeline was patched to enable distributed parallel processing and implement early data validation checkpoints. Automated alerts and documentation updated the response protocol for similar future incidents, ensuring much faster resolution and reducing business impact. What strategies do you use to reduce troubleshooting time and improve feedback loops during model deployment? Strategies include structured, granular logging throughout pipelines, detailed monitoring for all pipeline steps, and robust automated alerting for predefined anomalies. Maintaining clear, up-to-date runbooks and incident response protocols ensures a fast, coordinated team response. Integrating continuous improvement, such as frequent retrospectives and blameless postmortems, turns each issue into valuable process enhancements, boosting team readiness and deployment confidence over time. What are core best practices for securing data and models in an MLOps pipeline? Best practices begin with encryption of sensitive data at rest and in transit, using SSL or TLS for all communications. Implement role-based access control, RBAC for granular permissions, ensuring only authorized users access sensitive datasets or model endpoints. Perform regular security audits and vulnerability assessments, catalog pipeline dependencies, and automate threat detection using cloud-native tools. Deploy privacy-preserving measures like data anonymization, masking, or differential privacy, and store audit logs for all data and model access events. How do you ensure GDPR and data privacy compliance throughout the MLOps lifecycle? GDPR compliance is ensured through strong access controls, anonymization or pseudonymization of personal data, granting users rights like data deletion or correction, and clearly documented data usage. Retain data only for its required purpose, audit every access or transformation event, and design pipeline stages to support privacy by design principles. Tools like ML Flow and DVC can track data and model lineage for full auditability, while data processing agreements and regular reviews ensure ongoing conformance. What strategies defend against adversarial attacks and model poisoning in MLOps? Strategies include adversarial training, training models on adversarially perturbed data, input validation and filtering, regular robustness testing against crafted adversarial examples, and continuous monitoring for anomalous inputs. For model poisoning, strictly validate and authenticate all training data, apply data integrity checks, and implement monitoring pipelines to flag sudden drops in model performance, potentially linked to training data manipulation. How do you balance model performance, interpretability, and security in regulated industries? Balance is achieved by starting with simple, interpretable models as baselines and using explainability methods like LIME, SHAP for complex models. Regulatory standards may require prioritizing transparency over raw performance. Employ secure model serving techniques, careful model validation, and strong monitoring for both business and regulatory metrics. Engage stakeholders to clarify which requirements are non-negotiable. Examples are explainability in healthcare or finance, guiding tool and model choices accordingly. What is the role of serverless and cloud-native architectures in secure ML Ops delivery? Serverless platforms, example is AWS Lambda, and cloud-native services automate resource scaling, enforce security patches, and isolate workloads, thus minimizing operational risk. Enable rapid incident response, reduce infrastructure management overhead, and offer strong encryption and compliance features by default. For highly regulated workflows, use managed cloud environments with built-in compliance certifications tying together secure deployment, monitoring, and quick updates through automated, transparent CI/CD. Why is auditability critical in enterprise ML Ops, and how is it achieved? Auditability ensures that every model, dataset, and decision can be traced, reconstructed, and explained, a requirement in regulated industries and for troubleshooting. It's achieved with comprehensive logging, model and data versioning, persistent audit trails of training and deployment events, and by storing metadata about training context code, data splits, environment. Model registries, automated experiment tracking, and clear documentation enable auditors or stakeholders to review, validate, or challenge any result or deployment. What best practices maximize the traceability of models, data, and decisions in an ML Ops workflow? Key practices include version controlling not just code, but data and environment dependencies, using tools like DVC or ML Flow to log every experiment, maintaining model cards and data sheets to document key assumptions, provenance, and changes, tracking lineage, who trained the model, on what data, with which parameters, logging all predictions with relevant context, and linking model deployment events to configuration snapshots closes the accountability loop. How do you document and communicate model assumptions, limitations, and lineage at scale? At scale, documentation should be automated within pipelines. Model cards that outline algorithmic choices, data sources, assumptions, and known biases, data sheets for datasets, and structured experiment logs. Integrated dashboards and regular documentation reviews ensure details stay up to date. Automation lowers the operational burden and provides compliance or comprehension for technical and non-technical stakeholders alike. Describe how you'd set up automated approval, conformity, and compliance checks for regulated ML Ops deployments. Automated checks in CI and CD pipelines validate that all required documentation, metadata, logs, and model performance metrics are present and meet regulatory thresholds before deployment. Automated approval gates flag missing or outdated information, bias or fairness issues, or unexplained parameter changes. Conformity testing is repeated on every material change and is auditable via dashboards and persistent logs, meeting external audit or CE conformity certification requirements. What tools or design principles help guarantee that ML model decisions are always explainable and auditable? Combining interpretable modeling approaches, where possible, with comprehensive experiment tracking ensures traceability. Model registries, versioning, explainability libraries, like SHAP or LIME, and integrated dashboards capture outputs, attributions, and explanations for every prediction. Automation ensures that every training, testing, or inference instance logs its input, output, and relevant configuration, ensuring end-to-end traceability for technical reviewers and compliance teams. What is the importance of continuous improvement in ML Ops, and how is it implemented? Continuous improvement ensures that deployed models evolve with changing data, business objectives, and user requirements, preventing model staleness. It is implemented through proactive monitoring for model/data drift, automated retraining pipelines, continuous training or CT, and regular reevaluation of both performance and reliability. Feedback loops are established via performance tracking, business metric evaluation, and user-watch stakeholder input, integrating lessons learned into model updates and pipeline optimizations. As a result, systems stay accurate, relevant, and resilient. How does automation underpin successful ML Ops workflows? Automation is foundational to robust ML Ops. It replaces fragile manual processes with codified, repeatable pipelines for training, validation, deployment, and monitoring. CI and CD and CT orchestrate the entire lifecycle, enabling fast, reliable updates, reducing technical debt and risk, and speeding time to market. Automated feature stores, versioning, and drift detection reduce operational overhead and error rates, freeing teams to experiment, validate, and deploy at scale. What types of testing are critical to trust and reliability in ML Ops pipelines? Testing in ML Ops extends beyond software unit and integration tests. Comprehensive testing includes model validation, like accuracy, recall, precision, robustness checks, like against adversarial or noisy data, regression testing after retraining, and continuous monitoring for drift or bias. A B and canary testing validate new models in production with minimal user risk. Automated alerts on test failures and clear testing documentation support reliability and accelerate troubleshooting. How do cross-functional teams ensure efficient collaboration in enterprise ML Ops implementations? Efficient collaboration starts with clear communication channels, shared project goals, and transparent responsibility assignments. Using unified platforms for experiment tracking, model and data versioning, and workflow orchestration, both data scientists and engineers access shared artifacts and documentation. Agile ceremonies, like Scrum, retrospectives, and continuous feedback foster alignment. Frequent training and open communication loops help resolve blockers and embed best practices across technical and non-technical contributors. What role does continuous monitoring play in driving improvement and compliance in ML-powered applications? Continuous monitoring provides real-time insights into system health, model accuracy, latency, and business KPI impacts. Automated triggers detect drift, degradation, or anomalous results, enabling timely corrective actions, like retraining, rollback, or stakeholder alerts. Monitoring is also key for regulatory and audit readiness, supplying a data-driven trail for decisions and ensuring ML systems meet evolving compliance and performance standards in production. What are the typical causes of production model failures in ML Ops, and how do you proactively address them? Production failures often stem from data pipeline issues, data drift, schema mismatch, missing or noisy data, infrastructure outages like resource bottlenecks, configuration drift, code bugs or dependency updates, and model degradation over time. Proactively addressing these includes automated pipeline tests, schema validation, resource monitoring, dependency pinning, robust canary or blue-green deployments, and detailed failure alerting. Having playbooks and process documentation ensures rapid incident triage and response. Walk through a structured root cause analysis process for a model performance drop in production. Start by acknowledging the problem and gathering data. Review monitoring dashboards, pipeline logs, and system metrics for anomalies. Verify recent data profile changes. Was there drift, a new source, or a missing feature? Inspect recent code commits, dependency upgrades, or changes in the serving environment. Compare failing and healthy systems, example is staging. Once the underlying issue is identified, implement a targeted fix, test thoroughly, and communicate learnings with a post-mortem. Update monitoring, tests, and runbooks to prevent recurrence. How do you minimize the business impact of production ML incidents? Mitigation demands early detection with real-time monitoring, granular alerting, and clear escalation protocols. Use canary/shadow deployments, circuit breakers, and rapid rollback for high-risk updates. Maintain backup models, pre-computed results caches for critical services, and ensure that incident response is rehearsed through playbooks and disaster recovery drills. Transparent stakeholder communication and continuous improvement processes prevent repeated losses and maintain trust. What cross-functional challenges can make production failure resolution difficult in ML Ops? Key challenges include siloed teams like data, engineering, ops, unclear ownership of pipeline components, non-standard logging or monitoring, and communication gaps. Resolution improves when team structures and work practices systematically support collaboration, shared dashboards, clear on-call rotations, and open, blameless retrospectives. Investing in documentation and regular knowledge sharing helps all contributors respond effectively to incidents. How does continuous monitoring enable early root cause detection and higher ML system reliability? Continuous monitoring tracks data, model, and infrastructure metrics in real time, flagging issues before they impact end users. Integration with observability tools and automated root cause analysis helps pinpoint whether trouble stems from data, code, or environment. Regular reporting and proactive dashboard reviews create a feedback loop for ongoing improvements, reducing downtime and raising overall system resilience as ML products scale. What are the main architectural strategies for scaling ML Ops across global or multi-region deployments? Architectural strategies include modular, layered pipeline designs where each component, like data ingestion, pre-processing, feature generation, model training or serving, operates independently, enabling updates without disrupting the entire system. Global deployment leverages multi-region clusters, managed cloud services, and data replication to ensure low latency, redundancy, and disaster recovery. Automating CI and CD or CT, like continuous integration, delivery, and training across environments, dev, staging, and prod streamlines scalability and governance everywhere the system runs. How do you manage model consistency, compliance, and performance across regions? Consistency is ensured through centralized model and data registries, version control, standardizing pipeline steps, and automated artifact promotion processes. Compliance is supported by environment-level configuration for local privacy or regulatory rules, region-specific monitoring, and site audit trails. Ongoing benchmarking and business metric scoring in each region identify and resolve performance gaps, while automated retraining and rollback mechanisms synchronize updates globally. Documentation and communication between regional teams close the loop for governance and best practice sharing. What role does hybrid batch and streaming architecture play in modern enterprise ML Ops? Hybrid architectures combine batch, like efficient, large-scale offline processing, and streaming, like real-time or near real-time inference and retraining to balance speed and resource use. Streaming supports immediate predictions, drift monitoring, or event response, while batch jobs can retrain models with deep context or reprocess backlogs. Managing these architectures requires robust orchestration tools, modular workflows, and careful monitoring to ensure smooth integration, data correctness, and efficient scaling. How do you design for modularity and maintainability in ML Ops pipelines? Modularity is achieved by decomposing workflows into reusable pipeline components, like microservices, tasks, each with clear interfaces. Infrastructure as code, standardized AP and strong data/metadata tracking facilitate integration and swap out. Tests, monitoring, and documentation are integrated at every module boundary. This approach allows teams to experiment, scale, or replace models independently, minimizing risk and technical debt as projects and regions grow. What are the challenges of managing metadata and artifacts in large-scale cross-region MLOps operations? Challenges include ensuring consistency, like synchronization of model/data versions across all locations, low latency access to metadata or artifact stores, compliance with diverse regulations, and disaster recovery. Centralized or distributed but federated metadata stores manage experiment tracking, lineage, and artifact state. Automated tools and policies resolve version conflicts, log lineage and deployment state, and establish a reliable single source of truth for global collaboration and auditability. What are key risk categories in MLOps? and how do they impact enterprise ML projects? Key risk categories include data risks, examples are drift, leakage, privacy breaches; model risks, examples are overfitting, bias, adversarial attacks; infrastructure risks, like downtime, misconfiguration; and organizational risks, examples are lack of access controls or incident preparedness. Each can trigger business, regulatory, or security consequences, leading to legal penalties, revenue loss, or loss of trust. Proactively tracking, classifying, and prioritizing risks ensures that controls are planned and proportionate to potential impacts. What operational practices help minimize risk in production ML pipelines? Critical practices include encryption of all data in transit and at rest, role-based access control and audit logs, automated validation, schema, statistical, of every incoming dataset, regular security and dependency audits on all code and third-party packages, redundant monitoring with automated alerting for performance, security, and compliance thresholds, documentation, runbooks, and automated rollback plans for quick recovery. How do you respond to and recover from security incidents in MLOps environments? Preparation is key. Establish clear incident response protocols, monitor for anomalies in real time, and automate the isolation of compromised pipelines or endpoints. After detection, teams perform root cause analysis, restore from clean backups, and update both technical controls and team training. Conducting blameless postmortems documents lessons learned, drives process improvement, and ensures accountability without attributing blame. Which security best practices are especially important for ML model and data protection? Essential practices: use service principles and manage identities for authentication. Apply the principle of least privilege through RBAC and network isolation. Encrypt and digitally sign models and data. Monitor for data exfiltration or insider threats. Audit third-party models and supply chain dependencies for vulnerabilities before integration. How does a security mindset and strong culture reduce ML ops risk? A security-first culture ensures security isn't an afterthought. It's embedded throughout design, development, and deployment. This means regular security training, encouraging all teams to contribute to threat modeling, and involving security stakeholders in pipeline and architecture decisions. This approach increases awareness of emerging threats, ensures everyone understands protocols, and helps the organization as a whole detect and respond faster, reducing overall risk exposure. What are key challenges unique to LLM ops compared to classical ML ops? LLM ops introduces unique challenges, massive model sizes and infrastructure requirements, prompt performance variability, sensitive data exposure, and the need for real-time content moderation. LLM deployment often requires distributed inference, specialized hardware like GPU or TPU, and cost optimization for serving at scale. Versioning involves both model weights and prompt templates, while observability must capture nuanced output drift, bias, and hallucination incidents. Compliance and audit risk are amplified by generative unpredictability. How do you approach model versioning and rollback for large LLMs in production? Each model version, including weights, tokenizer, training hyperparameters, and prompt pipeline, is tagged and stored with metadata in a robust registry. As updates are often resource-intensive, canary or shadow deployment is used for real-world validation before full rollout. Rollback means switching endpoints back to previous weight plus prompt combinations, and robust logging ensures traceability in case of user complaints or policy violations. What additional monitoring is essential for LLM-powered applications versus traditional ML? Monitoring must include prompt input and output diversity, toxicity or bias flags, hallucination detection, and latency or jailbreak attempts in logs. Human-in-the-loop review is integrated for flag cases. Output distribution drift is monitored with continual feedback loops from both automated detection and user reporting, with policies for rapid response if models generate unsafe, nonsensical, or non-compliant outputs. How do you safely integrate LLMA PIS in open-source models in regulated industries? Integrate large language models behind secure API gateways, sanitize all external input and outputs, and use moderation and validation services. OpenAI, Anthropic, and Hugging Face models require additional on-prem or VPC deployments for privacy. All generations are logged and analyzed for compliance, and organizations often implement robust access controls, prompt content filtering, legal review for high-impact features, and incident response workflows for unsafe generations. What incident response mechanisms are important for handling LLM hallucinations or toxic content in production? Key mechanisms include real-time alerting on flagged content, user reporting and escalation pipelines, immediate blocking or rollback of problematic models or prompts, and rapid retraining or fine-tuning with incident datasets. Comprehensive event logging and root cause analysis drive continuous improvement. Human moderators are looped in for ambiguous cases, and clear communication to stakeholders limits reputational risk while addressing the root issue. What are best practices for incident response when large language models generate hallucinations or unsafe content? Immediate detection comes from real-time monitoring with automatic flagging, feedback integration, and user reporting pipelines. Incident playbooks, predefined for various case types, examples are hallucination, bias, toxic output, guide rapid triage and fix. Playbooks detail assessment, escalation, and communications. Shadow banning, output filtering, and, if necessary, reverting model or prompt versions are core tactics. All events must be logged, and postmortems drive updates to prompts, rules, or fine-tuning datasets as a continuous improvement loop. How can automation accelerate and standardize LLMOps incident response? AI observability and incident response automation use intermediate layers for telemetry, like logging user inputs, LLM outputs, errors, prompts, versions, and response times, to feed real-time dashboards and trigger alerting when issues arise. Automated prioritization and escalation integrated into tools like PagerDuty route incidents to the right experts, while runbooks and response playbooks enable fast, repeatable actions, even in large teams. Automated actions, examples are revoking prompts, switching to fallback models, take effect before human review for major severity incidents. What incident data should be collected and analyzed to inform future LLM deployments? Capture telemetry, including user input, LLM output, error logs, token usage, response time, and prompt/model versions for every event. Annotate incidents with user feedback and link flagged cases to post-incident review outcomes. Examples are retraining or fine-tuning, policy updates. Trace all incident handling steps to understand what responses worked and identify procedural, data, or model weaknesses for ongoing LLMOps system hardening. Why is human oversight still critical, even in automated LLMOps incident management? Automation handles common and clear-cut incidents quickly, but human expertise is essential for complex decisions, ambiguous cases, and policy adaptation in evolving regulatory contexts. Humans guide the refinement of automation, identify new risk patterns, and ensure that responses are appropriate, transparent, and sensitive to real-world nuance. Regular drills, training, and collaborative postmortems keep teams ready and response processes current. What ongoing practices help LLMOps teams learn and adapt from incident response cycles? Regular incident reviews and system simulations surface gaps in both runbooks and model controls. Feedback from users and responders integrated with LLM telemetry identifies blind spots or new threats. Standard operating procedures, SOPs, and playbooks are version-controlled, regularly updated, and shared. Trends from incident logs inform retraining, prompt engineering, and policy refinement, creating a virtuous cycle of safety, trust, and technical excellence in large-scale language model operations. What best practices should teams follow to automate incident response for LLM-powered systems? Begin with well-defined, high-impact, and common response processes, such as rolling back prompts, filtering outputs, or alerting stakeholders. Use playbooks codified for incident types. Examples are unsafe generations, system overloads, that map to automated workflows in your incident management platform. Ensure automation integrates with telemetry, SIEM, and collaboration tools for detection, triage, and remediation. Regularly validate workflows against real and simulated incidents, refine drifts, and update runbooks as threats and LLM capabilities change. Why is humans in the loop, HITL, essential, even with advanced LLM plus incident automation? Though automation accelerates routine triage, IHTL remains vital for nuanced judgment calls, such as evaluating content ambiguity, regulatory sensitivity, or user intent. Escalate complex or high-severity events to experts for manual review and action, documenting decisions. HITL ensures oversight for unprecedented cases and reduces the risk of automation blind spots, where contextual awareness and empathy matter most. What critical metrics should be tracked to improve LLMOps incident response? Key metrics include mean time to detection, MTTD, and mean time to recovery, MTTR, resolution rate, false positive rate, and escalation frequency. Output incident frequency by type, e.g. hallucination, jailbreak, bias. System health, latency, load, token usage during and after incidents. Tracking these metrics guides continuous automation tuning, resource planning, and targeted team retraining for optimal resilience. How do you ensure incident response automation adapts to evolving threats and LLM behavior? Adopt continuous learning, review incident logs for emerging patterns, conduct regular chaos engineering drills, and refine automation playbooks based on post-incident analysis. Integrate feedback from users, expert reviews, and new threat intelligence. Keep playbooks and workflows under version control and periodically validate with new LLM features or release cycles. This iterative approach keeps both detection and remediation sharp as systems and attack surfaces grow. Why is cross-team communication and documentation critical in LLMOps incident response? Centralizing incidents, actions, and context in a unified reporting and collaboration platform ensures all stakeholders, ops, security, engineering, compliance, have visibility and can coordinate on resolution. Postmortems, shared runbooks, and transparent status updates drive knowledge transfer, improve system learning, and facilitate regulatory readiness when rapid and accurate response to LLM-generated incidents is required. What are the main challenges in fine-tuning large language models, LLMs, within a production LLMOps workflow? Fine-tuning LLMs requires significant computation, expert prompt engineering, and sophisticated data curation to avoid overfitting or introducing bias. Operational challenges include resource management, like GPU or TPU scheduling, data governance, ensuring no sensitive or non-compliant data are included, and rigorous tracking of all changes for rollback or audit purposes. Security and privacy must be maintained throughout, with version checkpoints and robust evaluation on safety and business-specific performance before any promoted rollout. How should a team approach privacy risk when fine-tuning or serving LLMs on proprietary or sensitive data? Teams must segregate sensitive data, apply strong access control, and anonymize or pseudonymize records before use in fine-tuning. Logging, encryption, and differential privacy methods add extra safeguards. In production, prompt inputs and outputs must be monitored for data leakage, using automated detectors, HITL review, and regular compliance audits. Only the minimum required data should be stored, and endpoints should be isolated within secure networks. Which compliance and documentation measures are essential for responsible LLM ops in regulated industries? Maintain full lineage of data and model versions through centralized registries. Document prompt templates, model updates, training data sources, and evaluation criteria. Conduct bias and safety assessments on each version and log changes to prompts and filtering policies alongside all deployments. Compliance reviews must be documented with automated and manual approval gates to meet legal/regulatory standards for explainability, privacy, and safety. What are best practices for evaluating the effectiveness of LLM fine-tuning before production rollout? Develop a comprehensive, representative evaluation set covering intended use cases and edge case risks, including adversarial and user-generated prompts. Quantitatively measure key metrics, accuracy, relevance, safety, and bias, while running qualitative reviews with both experts and target users. Compare results with baseline and prior versions. Document all findings and require sign-off by interdisciplinary teams, engineering, compliance, business, before deployment. How do you ensure privacy-preserving inference when deploying large language models in multi-tenant environments? Isolate client data at rest and in memory, use per-tenant access controls, and audit logs for every model interaction. Deploy prompt and response filtering to prevent cross-tenant data leakage. Adopt encrypted communication, and consider secure enclaves or federated inference for highly sensitive domains. Proactively test for privacy breaches and require third-party compliance reviews for the LLMOps stack periodically to ensure ongoing privacy protection. What are the critical infrastructure considerations when scaling LLMs in enterprise environments? Enterprises must provision GPUs or TPUs at scale, implement distributed inference and training clusters, and invest in robust orchestration platforms for seamless model serving and rolling updates. Cost control requires auto-scaling, serverless endpoints, and model compression techniques. Resource allocation must be dynamically managed to meet fluctuating load without over-provisioning. Data pipelines must also scale with redundancy and monitoring to ensure reliable, high-volume model operation. How can LLMOps frameworks support cost optimization while maintaining performance and reliability? Use profiling to fit the smallest model that achieves business KPIs, leverage quantization, distillation, or LoRa for lightweight serving, and continuously monitor throughput and latency to avoid wasted compute. Batch processing, caching frequent responses, and elastic scaling reduce infrastructure spend. Centralized model registries and prompt versioning prevent error replication, while governance and prompt guardrails minimize the risk and expense of model failures in production. Why do many enterprises prefer private LLM deployment, and what are the main challenges of this approach? Private LLMs guard IP and sensitive data, supporting direct control over model retraining, monitoring, and compliance. The challenges include complex hardware management, dependency tracking, on-prem security, and integration of enterprise observability and compliance solutions. Building and securing these clusters requires cross-functional teams, explicit compliance controls, and careful coordination between data, infra, and model owners. What are proven best practices for orchestrating multi-model and multi-tenant LLM deployments at enterprise scale? Designed for modular, containerized deployments managed by orchestration frameworks, example is Kubernetes, centralized configuration and model registries, and version all prompts, adapters, and outputs separately. Use strong isolation between tenants, audit logs for every request, and automated fallback to backup models for resilience. Implement SLO monitoring to ensure both business and technical outcomes are met for each app and department on the platform. Describe the role of observability in managing and scaling large language models in production. Observability platforms aggregate logs, metrics, and traces from model infrastructure, applications, and LLM outputs, enabling rapid identification of bottlenecks, failures, or drift. Real-time dashboards allow engineers and business leaders to monitor system health, response quality, and prompt effectiveness. Proactive alerting means issues are detected early, enabling fast switching, scaling, or rollback actions, which optimize reliability and performance as demand and usage patterns shift. What are the primary quantitative metrics used for evaluating LLMs in production? Key production metrics include BLEU, ROUGE, and METEOR for text similarity, perplexity for language model fluency, and traditional Trinity metrics like accuracy, precision, recall, F1, for structured tasks. For unsupervised tasks, metrics like context recall, silhouette score, or Davies-Bouldin index are used. Real-time systems also monitor response time, token usage, and throughput, blending model accuracy with operational health for reliable, scalable outcomes. Why is human feedback and qualitative evaluation so crucial in LLMOps? Automated metrics often fail to capture nuance, output safety, or business context appropriateness. Teams integrate human-in-the-loop reviews, user feedback ratings, and golden prompt sets for real-world coverage. Qualitative A/B testing, scenario walkthroughs, and stakeholder sign-off provide a holistic sense of output helpfulness, factual correctness, and tone, key for trust and continuous improvement. How do you track and assess bias, toxicity, and ethical risks in production LLM deployments? Deploy automated detectors for toxicity, bias, and hallucinations, and regularly analyze flagged outputs by user demographic or use case segment. Integrate fairness and harm metrics, like disparate impact or toxicity scores, into dashboards. High-risk or edge case generations are manually reviewed, with documented sign-off on remediation, prompt or guardrail tweaks, and post-incident system tuning to sustain responsible AI in production. What is the role of contextual or extrinsic metrics in LLMOps? Extrinsic metrics measure model value on specific domain tasks or user journeys, task success rate, retention uplift, time to resolution, or cost per completed interaction. Contextual recall evaluates an LLM's ability to retain or correctly reference conversation history. These metrics align evaluation to business and practical value, going beyond technical measures for true impact. How do effective LLM Ops teams implement robust evaluation pipelines and benchmarks? Teams create automated, reproducible test suites with static, golden set, and dynamic ABC test prompts covering critical and risky scenarios. Evaluation integrates both automated and human scoring, and results feedback into continuous monitoring and reporting platforms. Regular reviews refresh prompt sets, incorporate new risk signals, and share learnings organization-wide for adaptive, ethical LLM evolution in real-world deployment. What are key architecture patterns for LLM Ops system fallback and disaster recovery? Robust LLM Ops architectures prepare for model, prompt, API, or infrastructure failures with layered fallback strategies. Automatic failover to backup/secondary models, progressive rollback to simpler versions or degraded service, and active-passive multi-region deployments for business continuity. Graceful degradation keeps core functionality available even during major incidents. Automated health checks, canary testing, and chaos engineering validate disaster recovery plans, while communication protocols and manual overrides are defined for critical failures. How do you implement a layered fallback system for LLM-powered applications? A resilient fallback system starts with multi-provider and multi-model support, leveraging an AI gateway or orchestrator to route requests. When the primary LLM provider or model fails, timeout, error, unsafe output, etc., the orchestrator automatically switches to a backup provider, a less powerful but more reliable model, or a predefined prompt response. Static timeouts, smart routing, schema validation on outputs, and retry backoff policies all minimize user-visible failures. What is the role of automatic retry and backoff in LLM Ops error recovery? Automatic retry mechanisms with exponential backoff address transient errors such as API rate limits, networking hiccups, or temporary infra issues. Rather than failing on the first error, the orchestrator defers the request and tries again, avoiding unnecessary traffic spikes or cascading failures. If multiple retries are unsuccessful, the next fallback tier, alternate provider or generated response, is activated, balancing resilience and cost. Why is runtime observability and structured logging critical for fallback and recovery? Every retry, route switch, failover trigger, and fallback event should be fully logged, along with root causes and remediation paths. Observability provides engineering, ops, and compliance teams with real-time insight into what's failing, why, and how well the system is recovering. It drives ongoing tuning, enables better incident investigations, and ensures that user experience remains consistent even under duress. Without this, failures can remain hidden, compounding future problems. How can AI agent systems build recovery paths for multi-step, tool-using LLM workflows? Modern LLM agents, which coordinate multi-step plans and external tool invocations, require schema validation, modular error handlers, retry wrappers, and escalation protocols to humans or specialized subsystems for persistent or critical failures. Chain of responsibility patterns, context re-verification, and semantic fallback prompts are used to avoid compounding errors in long plans. Comprehensive logging, targeted retries, and flexible recovery logic turn probabilistic, dynamic workflows into reliable, production-grade systems. What are the primary compliance drivers for LLM ops in enterprise environments? Enterprises face growing regulatory scrutiny from standards and laws, such as GDPR, CCPA, HIPAA, and sector-specific mandates, like BFSI, healthcare legal. These regulations require that organizations document data flow, protect customer and business data, and make LLM operations transparent and auditable. LLMOPS thus embeds documentation, audit trails, access controls, and monitoring into every stage from prompt versioning to inferencing and update workflows to proactively manage compliance risk. How does LLM Ops embed governance to minimize privacy and regulatory risk? LLM Ops automates the collection of logs for all model versions, prompt templates, and outputs. It restricts access to sensitive models and data via RBAC and strong authentication, regularly audits pipelines for data leakage or bias, and supports human-in-the-loop review for high-impact decisions. Encryption, anonymization, and prompt guarding are implemented where practical. Automated checks and approval gates ensure that only compliant, documented versions make it to production. What documentation and auditability measures ensure regulatory compliance in LLM ops? Best practices require automated model and prompt versioning, lineage tracking, like including datasets, model weights, configuration, and prompt and changes, and persistent logs for all access and updates. Compliance teams need access to model cards, data sheets, user/admin logs, remediation workflows, and proof of policy enforcement. These artifacts support audit readiness for both enterprise and external regulators and ensure safe, explainable LLM deployments. How should organizations handle privacy and PII when LLMs are exposed to customer-facing or sensitive prompts? Sensitive information, like PII or PHI, must be masked or redacted in prompts, logs, and outputs wherever possible. All LLM access should be authenticated, permissioned, and monitored. Data minimization ensures only what is strictly necessary for task completion is retained or processed. Encryption in storage and transit, robust key management, and regular privacy audits remain core enterprise controls. How does LLM OPS compliance posture differ from classical ML ops in practice? While ML OPS focuses on model pipeline reproducibility, version control, and performance, LLM OPS requires much tighter controls on prompt management, API routing, and dynamic guardrails due to the risks of generative output. Examples are hallucinations, data leakage. LLM ops must account for prompt or response audit trails, rapid rollback, and cross-functional compliance reviews integrated directly into development and release flows, meeting a higher bar for transparency, safety, privacy, and stakeholder involvement. How do you optimize the LLM ops deployment architecture for scalability and maintainability? Design for modularity, separating data handling, prompt engineering, orchestration, inference serving, and monitoring layers. Adopt containerization, like Kubernetes/Docker, CI and CD, and auto-scaling for compute. Use prompt/model registries, structured logging, and feature flags for safe rollouts. Employ multi-region failover and load balancing for global coverage. Edge deployment, vector databases, and quantized serving help balance cost, performance, and flexibility. What are best practices for LLM API or endpoint integration in enterprise applications? Define robust API contracts for inputs, outputs, and error handling. Validate user prompts and sanitize outputs for security and privacy. Employ timeout management, retries, and fallback routes. Log request and response metadata for traceability, and include metrics for latency, cost, and safety incidents. Gate deployments through QA stages and manual approval before full production use. How is governance embedded in enterprise LLM ops deployment? Implement automated pipelines where only models or prompts that meet defined performance, safety, and documentation criteria are promoted. Maintain audit logs and version histories for all assets. Enable RBAC on deployment tools and model endpoints, and involve compliance reviews on prompt templates and output filtering. Governance dashboards and approval gates ensure organizational and regulatory standards are met. What cross-team workflows support fast, safe LLM ops deployment scaling? Effective scaling needs clear delineation between DevOps, data science, security, and product roles. Shared artifacts, experiment tracking, documentation, and observability dashboards foster collaboration. Regular drills and reviews on deployment incidents, plus explicit feedback cycles, are built into CI and CD. Escalations and overrides are fast, well-documented, and part of engineered organizational readiness. How does data quality and governance impact performance in LLM ops? High-quality, diverse, and well-governed data are fundamental for achieving reliable, robust, and unbiased LLM outputs. Organizations must enforce deduplication, bias checks, and lineage tracking at ingestion and preparation. Poor or uncurated data directly increases hallucinations, drifts, and downstream task failure, making automated pipelines and rigorous quality gates essential to optimize model accuracy and resource efficiency. What fine-tuning and training techniques are most effective for efficient LLM ops? Techniques like parameter-efficient fine-tuning, examples are LoRa, QLoRa, PEFT, dramatically reduce the compute cost and memory need versus full model retraining. Model quantization and pruning improve inference speeds and lower infrastructure usage. Batch size and learning rate optimization, along with distributed or parallel training, using libraries like DeepSpeed, Hugging Face, help scale training for enterprise workloads while maintaining high model quality. How is real-time monitoring implemented to ensure LLM service health and cost control? Implement tools like Prometheus, MLflow, Grafana, or cloud-native dashboards for granular tracking of inference latency, throughput, token usage, error rates, and anomaly detection. Service-level objectives, SLOs, must be defined and tied to business KPIs. Visualize live performance metrics and integrate automated alerts for drift, bias, and infrastructure anomalies to facilitate timely remediation and cost management. What optimization practices help LLM ops teams balance speed and cost in production? Leverage pre-trained and distilled models whenever possible, deploy quantized or mixed precision versions for inference, and use API request batching and caching for common prompt patterns. Implement auto-scaling and load balancing to adapt to variable demand, and run regular profiling to right-size model instances. Where possible, adapt prompts and response handling workflows to reduce unnecessary compute without sacrificing task quality. How does LLM ops handle stochastic and non-deterministic behaviors in large language models? Use prompt engineering, output schemas, and response templates to standardize LLM outputs. Fix random seeds, manage temperature and top P sampling for reproducibility where strict determinism is required. Implement drift detection and output validation to identify consistency issues. Automated versioning and careful testing for each deployment, especially when provider models change dynamically, ensure stable, predictable user experience even with probabilistic models. What are the most common failure modes for well-empowered applications, and how are they mitigated? Frequent reliability risks include hallucination, inaccurate generations, stale knowledge, overconfident errors, latency spikes, and prompt drift. Mitigation combines robust prompt engineering, prompt version control, continuous regression/evaluation pipelines, performance monitoring for latency, errors, output validation, and scheduled prompt/model reviews. Human-in-the-loop review ensures early detection and remediation. Redundant architectures, canary deployments, and rapid rollback further reduce user impact during failures. How can organizations reliably identify and address latent LLM performance issues in production? Integrate live dashboards for key metrics accuracy, latency, cost, anomaly rates, and user experience feedback. Automated feedback loops collect user ratings and system logs, comparing outputs against golden test suites. Routine chaos engineering drills, simulating edge case failures, and drift analysis on real user data surface hidden risks. Combined with regular postmortems, this enables continuous model and prompt improvement cycles for reliability. What role does prompt engineering and versioning play in LLM reliability? Clear modular prompt design coupled with strict version control and systematic regression testing prevents regressions and simplifies troubleshooting. Prompts are tagged by use case, intent, and revision. Automated replay of production traffic against updated prompts detects drift or unintended side effects before release. This process ensures improvements are deliberate and reproducible, and that problematic prompts can be rapidly rolled back. How do feedback and pattern analysis lead to continuous improvement in LLM Ops reliability? Post-incident analytics, powered by LLMS, identify recurring issues, propose system or process fixes, and inform retraining or prompt curation. Regular review of metrics, mean time to detect/recover, alert false positives, incident recurrence, and incident retrospectives enable targeted process and automation upgrades. Every incident becomes an opportunity for data-driven learning, making enterprise AI systems more robust over time. Why is continuous observability and data curation fundamental to trustworthy LLM Ops? Observability, via distributed tracing, live dashboards, and strategic alerts, enables teams to quickly detect and isolate problems across multi-agent workflows or high-traffic deployments. Continuous data curation from production logs, feedback, and new sources keeps evaluation and retraining relevant, sustains performance, and proactively reduces the risk of drifts or bias over time. How should evaluation and deployment processes be structured to maximize reliability in LLM Ops? Thorough evaluation involves unit, integration, and batch testing with golden and adversarial examples. Automated CI and CD pipelines block promotion of new prompts and models until reliability benchmarks are met. Deployments employ live observability, automated and human scoring, rollback on anomalies, and staged rollouts like Canary or Blue-Green to minimize disruption. Continuous feedback and weekly drift reviews anchor a culture of ongoing reliability improvement. What are the main approaches to fine-tuning large language models for enterprise use cases? Common approaches include full fine-tuning, updating all weights for specific task alignment, parameter-efficient fine-tuning, example are LoRa, Q, LoRa, adapter training updating only targeted layers or parameters for efficiency, and transfer learning via multitask or sequential learning. Distillation creates resource-light, deployment-ready models that match larger LLM capabilities. Method selection balances performance, speed, and infrastructure constraints depending on use case, data, and compliance environment. Why is proprietary data so important for effective enterprise LLM fine-tuning? Fine-tuning with proprietary company data support logs, internal reports, code, customer emails, equips LLMs with context, domain language, and process logic unique to each business. This boosts relevance, accuracy, and trustworthiness of responses for specific tasks, compliance requirements, and user journeys. Domain adaptation ensures even generalist LLMs understand company-specific terminology, priorities, and edge cases. What are the critical data curation and preparation steps before fine-tuning an LLM? Collect and clean proprietary data, anonymize sensitive content, and format for task alignment. Examples are instruction response pairs, summaries, Q&A, code snippets. Segment for training, validation, and test, ensuring data diversity and label quality. Iterative data audits and feedback cycles are vital to prevent introducing biases or misalignments. Effective pre-processing and quality assurance maximize generalization and production safety. How can parameter-efficient tuning, PEFT, and quantization make enterprise LLM deployment more practical? PEFT methods, like LoRa or adapters, update a small subset of model parameters, greatly reducing compute needs, memory, and cost, while preserving core pre-trained LLM abilities. Quantization shrinks model size, 8-bit or 4-bit weights, for faster, cheaper inference. Combined, these enable scalable adaptation to evolving business tasks, even under tight infrastructure or budget limits, and simplify continuous update workflows. Outline a robust workflow for deploying a fine-tuned LLM into production at scale. Select a proven pre-trained base. Prepare or train on high-quality, use case-specific data like minimize PII, maximize domain coverage. Choose the minimal needed fine-tuning scope full, PEFT or distillation. Validate against holdout and edge case datasets for safety and business accuracy. Optimize via quantization and batches/E stream-friendly serving. Control access via RBAC, monitor and log all accesses/responses. Integrate into business systems, like API, chat analytics, and schedule regular review, evaluation, testing, and cycles based on live feedback. Why is continuous monitoring and improvement essential for enterprise LLM deployments? No LLM is ever truly final. Model drift, data shifts, and changing user needs degrade performance over time. Enterprises must set up real-time monitoring, like metrics on latency, accuracy, safety, cost. Gather explicit user feedback and track model drift. Continuous improvement keeps LLM outputs accurate, safe, and relevant, and drives long-term business value in rapidly evolving environments. What are core steps for implementing ongoing model updates and retraining? Establish pipelines to collect, filter, and annotate new data or feedback. Set thresholds or schedules for triggering full retraining or lightweight fine-tuning, balancing cost and quality. Use automated workflows with orchestration tools like Airflow/Kubeflow for ETL, model retraining, and validation. Validate new versions against holdout datasets and edge cases, then promote only if they improve target metrics versus live models. How do you align DevOps, QA, and business teams for effective LLM Ops continuous improvement? Foster regular cross-team reviews anchored on business KPIs, not just technical metrics. Use collaborative experiment tracking, shared dashboards, and clear escalation paths for issues. Engage QA for automation and edge case testing, while DevOps applies CI and CD methodology to both data and model updates. Document every release and improvement cycle and ensure updates are aligned with business needs and compliance requirements. What QA testing best practices enable ongoing LLM Ops performance assurance? Comprehensive testing includes unit, integration, and system-level validation. Build golden sets and adversarial examples. A/B test new models and prompt variants before and after release, and run user acceptance testing UAT for major feature or behavior changes. Automated tests and monitoring ensure regressions or drift are caught early. Regular test set refreshing and thorough coverage are crucial for long-term assurance. How do you drive incremental value and ROI from enterprise LLMs over time? Align continuous improvement cycles with business goals. Each model update should be justified by impact, improved user satisfaction, time/cost to resolution, or automation of new tasks. Run regular ROI assessments and postmortems on deployments. Optimize for both business and technical KPIs, and communicate clear metrics to stakeholders to justify further investment or realignment of AI initiatives. How can large language models enhance enterprise incident categorization and triage? LLMs can automatically analyze, categorize, and triage incident tickets or logs based on predefined business and technical ontologies. By continuously learning from historical incidents, they adapt categorization schemas, improving detection of recurring issues and prioritizing urgent cases. This automation speeds up detection to resolution pipelines, reduces manual intervention, and drives down mean time to respond and recover. What are best practices for prioritizing and responding to incidents in LLM Ops environments? Automated incident scoring, impact and urgency, robust SLOS error budgets, and integration with real-time monitoring tools allow organizations to efficiently route the most critical issues to the right teams. Escalation paths, on-call rotations, and clear incident ownership support streamlined response. Automated and templated communication ensures timely, precise updates for internal teams and stakeholders. In what ways can large language models automate and optimize the creation of incident response scripts? LLMS can learn from historical incident resolutions to automatically generate and optimize scripts for remediation examples, restart services, apply hotfixes, reconfigure systems. They can suggest improvements to remediation playbooks, chain relevant commands for multi-step fixes, or even serve as coding assistants for on-the-fly responses to new error patterns. How should the impact and fairness of LLM-driven incident management be monitored? Continuous monitoring of resolution accuracy, detection/false positive rates, response time, and user feedback is essential. Bias audits and fairness protocols review incident assignment and resolution logs to avoid codifying or amplifying operational biases, e.g., repeated deprioritization of edge services. Well-designed alerting and regular dataset reviews safeguard both operational equity and trust. Why are blameless postmortems, documentation, and continuous learning so valuable in enterprise LLMOps incident response? Structured, blameless after-action reviews foster a learning culture, help teams identify root causes, process gaps, and automation improvement opportunities. Systematic knowledge capture, like auto-generated incident reports, updated runbooks, and retraining of LLMs on new incident corpuses, enables teams to iterate on both technical solutions and communication, improving resiliency and user outcomes with every event. How are large language models used to automate incident categorization in prioritization in enterprise operations? LLMS analyze incident reports, tickets, and logs in real time. They map unstructured event data to a defined ontology for automatic categorization. By learning historical incident patterns and current context, LLMS adapt priorities based on impact, service dependencies, and urgency. This speeds up triage and ensures that resources are allocated directly to the most critical incidents, reducing SLA breaches and response fatigue for IT or SRE teams. What common incident response actions are automated using large language models and orchestration tools? Typical automations include restarting failed services, rolling back problematic deployments, running corrective database or application scripts, sending targeted notifications, and triggering remediation workflows aligned with incident type. Examples are applying firewall rules, scaling infrastructure. Playbooks and automation pipelines ensure rapid, repeatable response while logging actions for audit and root cause analysis. How do modern incident automation platforms support closed-loop LLM ops workflows? Platforms integrate monitoring, ticketing, and communication channels with LLM-powered analysis, so detection, categorization, acknowledgement, remediation, and resolution reporting are all linked. Automatic escalation, on-call routing, and dynamic playbook invocation close the loop. Every incident is handled swiftly, and feedback from each resolution improves future automation logic and LLM prompt design. Why is automated incident documentation or reporting an enterprise reliability game changer? LLMS can generate structured incident reports in real time, detailing root cause, steps taken, impacted systems, and outcome summaries, pulling from logs, scripts, and collaborative chat. This ensures forensic completeness, faster regulatory reporting, and clear knowledge transfer for postmortems or training. Automation also reduces gaps and delays, ensuring accurate incident histories. How does incident trend analysis with LLMS shape future ops for large organizations? LLMS identify recurring failure patterns, suggest proactive mitigations, and inform ops playbook updates. Incident trend insights enable leaders to target investment, refine alerting, and optimize cross-team workflows, ultimately reducing incident frequency and severity over time. Data-driven improvements compound, making each incident an active contributor to continuously strengthening organizational resilience. How are large language models automating incident categorization and adaptive prioritization? LLMS classify events and error logs based on context, mapping incident details to predefined taxonomies. Over time, they adapt categories and adjust prioritization based on business impact, urgency, and service dependencies. This not only speeds up first response, but ensures high-impact issues are surfaced for immediate action, reducing SLA violations. What types of remediation actions can be fully automated in modern LLM-enabled incident response? Orchestrated automations now handle service restarts, deployment rollbacks, execution of known hotfix scripts, alert or notification dissemination, credential rotation, and sandbox isolation. Workflow automation integrates with ITSM platforms, intelligently triggering playbooks for repetitive or clearly categorized incidents. So humans focus only on root cause and novel crisis management. How do automation frameworks ensure traceability and collaboration during incident response? Integrated tools, examples are Xmatters, PagerDuty, ServiceNow, automatically generate incident logs, status updates, and collaboration threads like Slack, Teams, and Zoom, tracking every action from detection to closure. This audit trail supports postmortems, compliance audits, and ensures all stakeholders have real-time visibility on resolution progress and outstanding actions. How does machine learning and LLM automation help with real-time incident detection and alert noise reduction? Continuous ML or LLM-based anomaly detection sifts through monitoring data, filtering out noise, and escalating only legitimate incidents. Adaptive alerting leverages learned patterns to raise the signal-to-noise ratio, while LLMs summarize and route actionable signals, ensuring teams are not overwhelmed by false alarms and can quickly respond to real threats. What impact do chatbots and virtual agents have on modern LLM ops incident management? Chatbots powered by LLMs provide on-demand resolution scripts, automating first-line support for common and repeatable incidents. They log conversational data for incident records, escalate to humans when ambiguity or risk is detected, and help gather root cause information, all while reducing manual intervention and increasing speed or coverage for global teams. What are the core components of effective LLM ops incident management? Key elements include rapid detection with live monitoring and alerting, fast and coordinated response via structured on-call and escalation protocols, root cause or impact diagnosis, often aided by LLM-powered log and context analysis, and thorough post-mortem review. Roles are clearly defined, like incident commander, technical lead, comms, and regular drills reinforce readiness. Incidents are categorized by defined severity based on business impact, and workflows are documented and practiced in real-world and simulation settings. How does automation transform modern incident management for LLM-powered systems? AI-driven automation routes alerts, runs diagnostics, applies quick fixes, sends real-time status updates, and logs all actions automatically. Advanced platforms use event orchestration and conditional logic to trigger self-healing actions. Autoscale, fallback, sandbox, or escalate to an expert. This automation cuts manual effort, speeds up mean time to repair, reduces human error, and creates comprehensive instant documentation for audit and learning. Why is detailed incident documentation and postmortem review crucial in LLM ops? Accurate timelines and root cause logs help teams learn from each incident. Postmortems drive continuous improvement, updating playbooks and closing feedback loops. This prevents recurrence, shares institutional wisdom, and supports regulatory or safety readiness. Detailed documentation, actions, decisions, and communications is invaluable for onboarding, audits, and operational trust. How does modern incident software support end-to-end management in LLM ops? Enterprise platforms now support the full incident lifecycle, from anomaly detection with LLM-specific monitoring, through automated triage and correlation, to on-call and chat integration, status updates, and root cause analytics. Top tools offer resilient SLAS, flexible automation, multi-channel outreach, and seamless integration with the AI stack, enabling both routine and novel event management at scale. How do large language models enable smarter, faster categorization and escalation of IT incidents? LLMs can automatically read, classify, and triage incident tickets or alerts based on predefined business and technical schemas, leveraging historical log analysis to adapt to emerging issues. Their ability to parse unstructured logs and contextualize alerts enables faster, more accurate assignment and prioritization, streamlining the overall incident response pipeline. Becomes an opportunity for data-driven learning, making enterprise AI systems more robust over time. Thanks for watching. If you found these 200 ML Ops and LLMOps interview questions helpful, don't forget to like, share, and subscribe for more in-depth AI tutorials and interview prep guides. Drop your toughest AI operations questions or interview experiences in the comments. We'd love to hear from you and keep this learning community growing. For more expert content on artificial intelligence, large language models, and production-grade ML, check out the links in the description below. Good luck with your next interview, and remember, in the world of AI, continuous learning and hands-on practice are your greatest superpowers. See you in the next video.